Have you ever wondered if we're alone in the universe? What if I told you that right now, at this very moment, a robot the size of a car is drilling into ancient rocks on another world, searching for the answer to one of humanity's most profound questions: has life ever existed beyond Earth? In September 2025, that robot may have found the answer. Join me on a journey to Mars, the red planet, a world of towering volcanoes, planet-wide dust storms, and ancient rivers that once flowed across a surface we now know was habitable for perhaps 1 billion years. For the next hour, let's travel together across 140 million miles of space to explore our most intriguing neighbor and discover why Mars might just rewrite everything we thought we knew about life in the cosmos. From Earth, Mars appears as a brilliant red star, brighter than almost anything else in our night sky. Ancient civilizations saw blood in that crimson glow and named it after their gods of war. But you and I, we know the truth is far more fascinating than mythology. That red color you see isn't blood or war, it's rust. Imagine an entire planet the size of all Earth's continents combined, covered in a layer of iron oxide so fine it could pass through your fingers like talcum powder. For billions of years, iron-rich rocks on Mars have been slowly oxidizing, creating a world permanently stained the color of rust. This is our first glimpse of a planet fundamentally transformed by chemistry, time, and the absence of one crucial element Earth takes for granted: a protective magnetic field. Let me share something remarkable with you. In February 2025, scientists discovered that the dominant mineral creating Mars's red color isn't what we thought for decades. It's not simple rust, but ferrihydrite, a special form of iron oxide that has water molecules locked inside its crystal structure. Think about that for a moment. The very dust that gives Mars its color is a chemical fingerprint of an ancient world where water once interacted with iron under cold, wet conditions billions of years ago. Every grain of Martian dust tells a story of a planet that was once dramatically different than the frozen desert we see today. You're not just looking at a red planet, you're looking at a geological record written in rust. Here's what makes Mars truly unique. This planet contains more than double the iron oxide in its outer layers compared to Earth. While our planet's iron sank deep into the core during formation, Mars's weaker gravity and smaller size couldn't pull all that iron down. The result? A world where 18% of the outer crust is iron oxide compared to just 8% on Earth. Picture a desert stretching as far as you can see in every direction, every rock, every grain of sand, every cliff face painted in shades of rust. But look closer with me and you'll see Mars isn't uniformly red. There are ochres and golds, burnt oranges and tans, browns and deep crimsons shifting across the landscape like an alien sunset frozen in stone. Look up at the Martian sky with me and prepare for your sense of normal to shift. While Earth's sky glows blue because our atmosphere scatters blue light, Mars does the opposite. Fine, rust-colored dust particles suspended in the thin atmosphere scatter red photons, creating a sky that appears salmon pink to butterscotch during the day. You'd stand on rusty red soil under a pink sky, watching blue-tinted sunsets as the physics of light scattering reverses everything you know from Earth. Even the dust itself is extraordinary, particles less than 1 This is a world transformed by time into something uniquely beautiful. The dust layer on Mars tells a story of planetary evolution spanning eons. Global dust storms, occurring on average every 5.5 Earth years, have been distributing this fine material across the entire planet for billions of years. The result is a remarkably uniform coating ranging from millimeters to 2 full meters deep in some locations. Imagine standing on a world where beneath your feet lies a geological archive. Just centimeters down, the rust gives way to distinctly brown soil, revealing layers of Martian history like the pages of an ancient book. Every layer represents a different era, a different climate, a different Mars. This isn't just a planet, it's a museum of its own transformation, preserved in rust and waiting for us to read its secrets. What transformed Mars from a potentially blue, water-rich world into this rusty desert? The answer lies in a catastrophic loss that happened billions of years ago. Mars's core cooled early, shutting down the global magnetic field that once protected the planet. Without that invisible shield, charged particles from the solar wind struck directly into the atmosphere, molecule by molecule, stripping it away to space over millions of years. As the atmosphere thinned, liquid water could no longer exist on the surface. It evaporated, froze into the soil, or disappeared into space. And in its wake, the iron-rich rocks began their slow oxidation, turning red in the presence of whatever thin atmosphere remained. You're looking at a world that lost its protection and paid the price in transformation. Today, Mars's rust-red surface receives more solar radiation than Earth's surface would at the same distance from the sun, because that thin atmosphere provides almost no protection. Yet there's a haunting beauty in this transformation. The very rust that speaks of loss also preserves the geological record better than Earth ever could. Without plate tectonics, without heavy weathering, without oceans to erode the past away, Mars keeps its secrets visible on the surface. Every ancient riverbed, every impact crater, every volcanic flow remains nearly as it was billions of years ago. In losing its atmosphere and turning red, Mars became something precious. A time capsule of the early solar system, waiting 4.5 billion years for someone to come and read its story. And now, finally, we're here to listen. As we prepare to journey deeper into this rust-red world, take a moment to appreciate what you're seeing. This isn't just a planet that happens to be red. This is a world whose color tells the story of its evolution, its loss, and its transformation. Every shade of crimson, every grain of rust-colored dust, every pink-hued sky is evidence of a planet that once had water, an atmosphere, and the potential for life. The red you see isn't a simple color. It's a 4 billion-year-old chemical signature of planetary change. And now that we understand why Mars is red, we can truly appreciate the magnitude of what we're about to explore, the towering volcanoes, canyon systems, and ancient waterways that shaped this remarkable world. Imagine standing on a plain looking toward the horizon. Slowly, impossibly, a mountain begins to rise. It keeps rising, and rising, and rising, and rising higher still, until its summit pierces so far into the sky that it extends beyond most of the atmosphere itself. This is Olympus Mons, and nothing in your experience on Earth has prepared you for its scale. At nearly 22 kilometers tall, this volcano is 2.5 times taller than Mount Everest. If you could somehow place it on Earth's surface, commercial aircraft would fly at altitudes lower than its summit. This single mountain is 100 times more massive than Hawaii's Mauna Loa, Earth's largest volcano. Welcome to the most colossal mountain in the entire solar system, a structure so vast it defies human comprehension. Here's what truly boggles the mind. Olympus Mons isn't just tall, it's vast. The base of this volcano spans 600 kilometers across. If you stood at its center, both edges would lie beyond your horizon. To walk around it would take weeks. The entire country of Italy could fit comfortably on its slopes. Or think of it this way. The state of Arizona could nestle entirely within its base, with room to spare. This mountain covers 300,000 square kilometers of Martian surface. Yet despite these staggering dimensions, the average slope is only 5%. If you were climbing Olympus Mons, it wouldn't feel like scaling a mountain at all. It would feel like hiking up an endless, gentle grade that just keeps going, kilometer after kilometer, for days. At the summit of Olympus Mons lies something equally spectacular, a complex of 6 nested calderas, each one formed when the magma chamber beneath emptied and the ground collapsed inward. These aren't small features. The caldera complex spans 60 by 80 kilometers and plunges more than 3 kilometers deep. Manhattan Island could disappear inside one of these chasms. The walls are steep cliffs of layered volcanic rock, each layer representing a different eruption, a different age, a different moment in this volcano's billions of years of history. Standing at the rim, looking down into these vast pits, you'd see darkness swallowing the bottom, shadows so deep that even Mars's thin atmosphere creates a haze obscuring the floor far below. These are the scars of a mountain that built itself through fire. Surrounding the entire base of Olympus Mons is a feature called the basal escarpment, essentially, a cliff that encircles the whole volcano. In places, this cliff towers 8 kilometers high. Imagine an 8-kilometer tall wall stretching hundreds of kilometers in each direction, formed where the weight of the volcano caused the surrounding crust to buckle and break. How did such a monstrous structure form? The answer lies in 3 factors unique to Mars. First, no plate tectonics. The volcano remained stationary over its hotspot for billions of years, allowing lava to accumulate in one spot rather than creating a chain of islands like Hawaii. Second, weaker gravity, making it easier for magma to rise and for tall structures to stand without collapsing. Third, unimaginable time. Olympus Mons grew slowly, roughly 1,000 times slower than Earth's volcanoes. The most recent eruption of Olympus Mons occurred just 25 million years ago. Think about that. When this volcano last erupted, early apes were walking on Earth. Some lava flows may be as young as 2 million years old, which in geological terms is practically yesterday. This means Olympus Mons might not be extinct at all, just sleeping in its very quiescent episodic pattern. It could erupt again. The volcano formed during the Hesperian period, about 3.5 billion years ago, through thousands of highly fluid basaltic lava flows. Each eruption would have sent rivers of molten rock down those gentle slopes, flows that could travel hundreds of kilometers before cooling. Layer upon layer, flow upon flow, the mountain grew higher and wider over timescales that dwarf human history. This is what patience looks like on a planetary scale. At the summit of Olympus Mons, atmospheric pressure drops to just 72 pascals, about 12% of Mars's already thin average surface pressure. This is essentially the edge of space. You'd be standing above most of the atmosphere looking down at clouds below you. The sky would appear darker, more stars visible even during the day. The temperature would be frigid, even by Martian standards. From this height, you could see the curvature of the planet clearly. On a clear day, if such a thing exists on Mars, you might glimpse other massive volcanoes hundreds of kilometers away. You'd be standing higher than any human has ever stood on any world, on a summit that took billions of years to build and may yet awaken again someday, sending lava flowing down slopes that stretch beyond the horizon. Olympus Mons doesn't stand alone. To the southeast lie three companion giants arranged in a line, the Tharsis Montes. Its greatest Mons rises 18 kilometers high, making it the second tallest mountain on Mars. Pavonis. Mons reaches 14 kilometers and sits precisely on the Martian equator. Arsia Mons towers approximately 20 kilometers with a summit caldera 110 kilometers wide. Each of these mountains dwarfs any volcano on Earth. Each has a diameter of 350 to 400 kilometers. The entire Hawaiian island chain from Kauai to Hawaii could fit inside a single one of these volcanoes. Together with Olympus Mons, these four giants created so much mass that they actually caused Mars's entire outer crust to shift roughly 20 degrees about 3 billion years ago. That's how heavy these mountains are. They changed the planet's orientation in space. The Tharsis region. This massive volcanic plateau stands 7 to 10 kilometers above the Martian datum, a reference level similar to Earth's sea level. The region contains 12 large volcanoes and represents the most intensely volcanic terrain on the planet. The sheer mass of Tharsis didn't just tilt the planet, it affected climate, rerouted ancient rivers, and shaped the evolution of the entire Martian environment. As we leave these titanic mountains behind and continue our journey, remember, these volcanoes aren't just geological features. They're monuments to the power of planetary forces operating over billions of years. They're proof that on Mars, even mountains dream bigger than anything we've seen on Earth. And they're still here, still waiting, possibly still capable of awakening. If Olympus Mons is Mars's monument to height, then Valles Marineris is its testament to depth and scale. Imagine a crack in the ground so vast it runs a quarter of the way around the planet. Stretch your mind and picture a canyon system extending 4,000 kilometers from end to end, the distance from Los Angeles to New York. At its widest, this gaping wound in the Martian crust yawns 200 kilometers across. At its deepest points, it plunges 7 to 10 kilometers below the surrounding plateau, with some locations reaching 11 kilometers down, making it the lowest elevation point in the entire system. This is Valles Marineris, the Grand Canyon of Mars, except the comparison is laughable. This system is 10 times longer and 5 times deeper than Earth's Grand Canyon. Stand in its center, and both walls would disappear beyond your horizon. Let me help you grasp the sheer magnitude of Valles Marineris. If you could drive along its length at highway speed 100 kilometers per hour without stopping, it would take you 40 continuous hours. Mount Everest, Earth's tallest mountain at nearly 9 kilometers, could be dropped into the deepest parts of this canyon and would disappear with 1 to 2 kilometers to spare before reaching the rim. The Grand Canyon, that icon of terrestrial geology, measures 446 kilometers long, 29 kilometers wide at maximum, and just under 2 kilometers deep. Valles Marineris could swallow it 10 times over in length alone. You could fit the entire Grand Canyon into just one section of one of Valles Marineris' many chasms and still have room left over. Canyon? This is a tectonic wound. Unlike the Grand Canyon, which was patiently carved by the Colorado River over millions of years, Valles Marineris formed primarily through catastrophic tectonic faulting. Picture this, about 3.5 billion years ago, as the massive Tharsis volcanic bulge to the west was forming, immense pressure built up beneath the crust. Magma pushing upward from below caused the entire region to rise and dome outward. The surrounding crustal rocks stretched like skin pulled tight over swelling, and finally they cracked. Enormous fault lines opened in the surface, and the ground between them collapsed downward into structures called gravens. This wasn't gradual erosion. This was the planetary crust breaking apart under stress. Imagine standing on solid ground when suddenly the terrain ahead of you drops away 10 kilometers in a series of catastrophic earthquakes. That's how Valles Marineris was born, but the story didn't end with the initial faulting. Once these great cracks opened in the surface, other forces took over. Underground water, locked in the porous rock and soil, found escape routes through the fractures. As this groundwater seeped out, it undermined the canyon walls from below through a process called sapping, causing huge sections to collapse. Then came the landslides, massive beyond anything witnessed on Earth. Steep, newly exposed walls became unstable. Enormous flank collapses sent billions of tons of rock and debris sliding down into the depths, widening the canyon to its present immensity. You can still see the landslide deposits throughout the system, frozen in place, some of them extending dozens of kilometers from the walls where they originated. Limited water erosion contributed too, with mineralogical data showing that water altered this terrain hundreds of millions of years ago. Valles Marineris isn't a single canyon but a complex system comprising multiple distinct chasms, each with its own character. At the western end lies Noctis Labyrinthus, a maze-like network of intersecting canyons creating a chaotic terrain of ridges and valleys. Then come the main chasms stretching eastward, Tithonium, Ias, Melas, Candor, Ophir, and Coprates. Coprates. Chasma alone extends 966 kilometers. In the east, the canyons of Ganges, Capri, and Eos gradually transition into chaotic terrain, leading to the Chryse-Planitia Basin, where ancient floods may have once carried water from the canyon system to lower elevations. Each chasm tells a slightly different story of formation, collapse, and transformation. Together, they form a network of interconnected valleys cutting across a vast swath of Mars. Stand at the rim of Valles Marineris, and you'd see something extraordinary. The canyon walls reveal billions of years of Martian geological history in steep, layered cliffs that drop into darkness. Each layer is a page in the planet's autobiography. Some layers are ancient volcanic flows. Others are sedimentary rocks deposited by wind or water. Some show signs of alteration by groundwater. The walls display this history in bands of different colors: rust reds, dark browns, lighter tans, occasionally even greenish or bluish tints where different minerals are exposed. Geologists dream of such exposures. On Earth, you'd need to drill kilometers down to see what Mars displays here openly in the cliff faces. The depth of the canyon creates such pressure differences that fog has been observed, forming on canyon floors at dawn, evidence of subsurface water ice and atmospheric conditions significantly different from the rim. Imagine descending into Valles Marineris, climbing down those layered walls. As you go deeper, atmospheric pressure would gradually increase. The temperature might shift slightly. Light would change as the walls rise on either side, eventually blocking the horizon. Hours or even days into your descent, the floor would finally appear below you. Down here, in the depths, the environment is subtly but significantly different from the plateau above. This is one of the lowest elevations on Mars, where the thin atmosphere is slightly less thin, where morning fogs can form, where the temperature variations might be less extreme. Scientists speculate that if liquid water exists anywhere on or near Mars's surface today, it might be in locations like these deep canyons where pressure and temperature conditions are marginally more favorable. As we prepare to leave this magnificent scar and continue our journey across Mars, take one last look at Valles Marineris. This canyon system is more than just a geological feature. It's evidence of planetary scale forces that literally ripped the crust apart. It's a window into billions of years of Martian history. It's proof that Mars, despite its small size and current frozen state, was once geologically active and dynamic enough to create structures that dwarf anything on Earth. If you could stand at its rim as the sun sets, watching shadows deepen in that impossibly vast chasm while the pink sky darkens overhead, you'd understand viscerally what it means to stand on another world. You'd feel the weight of deep time, the power of planetary forces, and the humbling scale of a cosmos far larger than our everyday experience suggests. Take a deep breath right now. Feel your lungs fill with air, that wonderful mix of nitrogen and oxygen that keeps you alive without you even thinking about it. Now imagine if that air was suddenly reduced to less than 1% of what you just breathed. That's Mars. The Martian atmosphere is so thin it's almost indistinguishable from the vacuum of space. Average surface pressure measures just 600 pascals, only 0.6% of Earth's sea level pressure. To experience equivalent pressure here on Earth, you'd need to ascend to 35 to 45 kilometers altitude, well above commercial aircraft cruising altitude, into the stratosphere where only specialized high-altitude aircraft and weather balloons operate. This isn't an atmosphere in the way we understand it. It's a whisper, a ghost, a fading memory of something much thicker that once existed. What little atmosphere Mars retains consists almost entirely of carbon dioxide, 95% by volume, with nitrogen making up less than 3%, argon about 2%, and oxygen a mere 1/6 of 1%. Trace amounts of water vapor, carbon monoxide, and other gases complete the mixture. The total mass of Mars's entire atmosphere is 2.5 times 10 to the 16th kilograms. That sounds like a lot until you realize Earth's atmosphere outweighs Mars's by a factor of 200. Imagine the entire gaseous envelope surrounding a planet weighing only 0.5% of Earth's air. You could almost think of it as the planetary equivalent of an exhaled breath, slowly dissipating into space. And in fact, that's essentially what's been happening for billions of years. Mars has been exhaling its atmosphere into the cosmos. Mars wasn't always this way. Compelling evidence suggests the red planet once possessed a much denser atmosphere, thick enough to support liquid water flowing across its surface for perhaps hundreds of millions or even billions of years. What happened? The answer is both simple and tragic. Mars's core cooled early in the planet's history, shutting down the global magnetic field that once protected its atmosphere. Without that invisible shield, the solar wind, a stream of charged particles flowing constantly from the sun, began striking directly into the upper atmosphere. These energetic particles literally knocked atmospheric molecules into space through a process called sputtering. Molecule by molecule, atom by atom, the atmosphere was stripped away into the void. This wasn't a quick process. It took millions of years. But it was inexorable. NASA's MAVEN spacecraft, orbiting Mars since 2013, has been studying this atmospheric loss in real time. The findings are sobering. MAVEN measurements show that 65% of Mars's argon has been lost to space through solar wind sputtering. Isotopic evidence reveals the magnitude of the loss. The deuterium to hydrogen ratio in Mars's atmosphere is 5 to 8 times higher than Earth's, indicating that Mars has lost massive amounts of water, with the lighter hydrogen isotopes escaping preferentially into space. Heavy nitrogen 15 is enriched, showing lighter nitrogen. 14 escaped more easily. Carbon isotope ratios suggest at least 50% of atmospheric carbon has been stripped away. During the late heavy bombardment period about 4 billion years ago, massive impacts may have removed up to 99% of the early atmosphere in explosive blasts. The thin atmosphere creates temperature swings that would be instantly lethal to unprotected humans. Mars's global average temperature hovers around -60 Celsius, -80 Fahrenheit. But extremes tell the real story. Temperatures can reach a pleasant 20 degrees Celsius, about 70 Fahrenheit, near the equator at noon in summer. Yet at the winter polar caps, temperatures plunge to -143 Celsius, negative 225 Fahrenheit. A typical equatorial location experiences temperature swings of 100 Kelvin or 180 degrees Fahrenheit from day to night. There's an old saying about Mars: you could stand at the equator at noon with spring at your feet and winter at your head. At ground level, the temperature might be above freezing, while your head, just 2 meters higher, remains in sub-zero conditions. With such a thin atmosphere, you might wonder, does Mars have weather? The answer is yes, but it's weather unlike anything we experience on Earth. Winds can reach impressive velocities during dust storms, 17 to 30 meters per second, up to 100 kilometers per hour at peak events. But here's the fascinating part. Because the atmosphere is only about 1% of Earth's density, even a 100 kilometer per hour wind exerts far less force than the same speed would on Earth. A Martian hurricane wouldn't knock you over, it would feel more like a stiff breeze. The real power of Martian winds isn't in their force, but in their ability to lift and transport the incredibly fine dust particles that coat the surface. When those particles start moving, they can create something spectacular: planet-wide dust storms. Clouds do form on Mars, though they're nothing like Earth's fluffy cumulus formations. Water ice clouds create wispy, cirrus-like patterns at high altitudes, most commonly over the major volcanoes as winds rise over the peaks. The aphelion cloud belt forms seasonally, stretching from Olympus to Elysium. Polar hoods, broad water, ice cloud formations shroud the winter poles like cosmic blankets. But Mars also has something unique: carbon dioxide ice clouds. In the polar regions during winter and at very high altitudes in tropical regions, temperatures drop below COIC's frost point of minus 125 Celsius. Carbon dioxide freezes directly from gas to solid, creating clouds of dry ice crystals. The Phoenix lander even detected COP snow falling from these clouds, though some of it sublimates back to gas before reaching the ground in a phenomenon called virga. Mars continues losing atmosphere to this day, though at much slower rates than during the planet's youth, when the young sun burned brighter and the solar wind raged more intensely. The process is ongoing, but measured in millions of years rather than human lifetimes. Some scientists propose that if we ever wanted to terraform Mars, make it habitable for humans, we'd need to somehow restore its magnetic field or continuously replenish the atmosphere faster than it escapes. It's a daunting challenge. But understanding why Mars lost its atmosphere teaches us something profound. Planetary habitability is fragile. A magnetic field, something we barely think about on Earth, is the invisible shield that keeps our world wrapped in breathable air. Mars lost that protection, and over billions of years, it lost the very air itself. The thin whisper that remains is all that's left of a world that once breathed deeply. Picture a world-ending apocalypse in slow motion. The sky begins to darken at midday. A wall of churning dust appears on the horizon, rising kilometers into the atmosphere. Within hours, day becomes twilight. Within days, the sun is reduced to a faint smudge of light barely visible through the thickening haze. The storm grows, spreading across continents, jumping between hemispheres, until finally the entire planet disappears beneath a swirling shroud of suspended dust. This isn't science fiction. This is what happens on Mars every few years when regional dust storms merge and escalate into planet-encircling global dust events. It's one of the most spectacular weather phenomena in the solar system, and nothing quite like it occurs on Earth. Welcome to the dust storms of Mars, where weather operates on a planetary scale. Let's start with the smaller storms to build our understanding. Local dust storms on Mars, roughly 1,000 square kilometers in extent, occur about 2,000 times per Martian year. These are relatively minor events, localized dust devils and regional wind patterns lifting dust for days before settling. Then come the regional storms, massive events covering over 1.6 million square kilometers, up to 1/3 of the entire planet. These can persist for 3 weeks or more and occur multiple times each Martian year, especially during southern spring and summer when Mars is closest to the Sun and temperature differences drive stronger winds. But even these impressive storms pale compared to what happens when conditions align perfectly and the regional storms begin to merge through positive feedback loops. That's when the real spectacle begins, the formation of a global dust storm. On average, once every 3 Martian years, about 5.5 Earth years, the perfect conditions arise. A regional storm begins lifting dust. The suspended dust absorbs sunlight and heats the atmosphere, creating temperature differences that drive even stronger winds. Those stronger winds lift more dust, which heats the atmosphere further, creating a positive feedback loop that can spiral out of control. The storm spreads. Other regional storms merge with it. Like a contagion, the dust propagates across the globe. The 2018 global dust storm covered approximately 15.8 million square miles, the combined size of North and South America. Dust extended up to 60 kilometers into the atmosphere. From space, Mars became featureless, a uniform rust-orange sphere with no surface details visible whatsoever. The entire planet had disappeared beneath the veil. The 2018 storm had a casualty, NASA's Opportunity rover, which had been exploring Mars for 14 incredible years. As dust blocked sunlight, Opportunity's solar panels could no longer generate power. The rover sent its final transmission on June 10, 2018, and never woke up again. Engineers tried for months to re-establish contact as the storm cleared, but Opportunity remained silent, its mission ended by the very dust that had been the subject of so much of its research. It's a poignant reminder that even though Martian dust storms wouldn't physically harm you, despite their impressive winds and planetary scale, they can be deadly to solar-powered equipment. The storm blocked enough sunlight that surface temperatures dropped despite the dust-heated upper atmosphere. When the storm finally cleared months later, Opportunity lay buried under a coating of fine dust, its mission complete. Not all Martian dust movement happens in massive storms. Dust devils, those spinning vortexes of air and dust, appear commonly across Mars, especially at 60 degrees north and south latitude during spring and summer. These convective vortices form when intense surface heating creates unstable air that rises in a tight spiral. On Earth, dust devils are typically tens of meters in diameter and might reach a kilometer high. On Mars, they're typically tens of meters wide too, but they can tower several kilometers into the thin atmosphere. Over major volcanoes like Mons, dust devils can reach extraordinary heights of 15 to 30 kilometers, far higher than any weather phenomenon on Earth except the highest thunderstorms. The Mons spiral dust cloud is a massive recurring feature that towers 15 to 30 kilometers above the volcano, visible from orbit. These countless dust devils are more than just beautiful curiosities. They're major contributors to the dust cycle. Collectively, they lift approximately 2.3 times 10 to the 11th kilograms of dust annually, comparable to the contribution of regional storms. They're also beneficial in an unexpected way. Rover missions have discovered that occasional close encounters with dust devils actually clean solar panels by blowing accumulated dust away. Imagine the engineer's relief when Spirit and Opportunity would suddenly show increased power generation after a dust devil passed overhead, sweeping away weeks or months of dust accumulation. The rovers were literally being cleaned by Martian whirlwinds. It's one of those serendipitous discoveries that makes Mars exploration so fascinating. The same dust that threatens missions can sometimes help them when the winds blow just right. Living through a Martian global dust storm from the surface would be an eerie experience. The sky would darken progressively over hours and days, taking on a deeper and deeper orange-brown hue as dust density increased. Temperature swings would moderate slightly. The night wouldn't get quite as cold, and the day wouldn't get as warm because the dust acts as both a sunblock and an insulating blanket. visibility would drop dramatically. Eventually, you might not be able to see more than a few dozen meters in any direction. The dust would be everywhere, infinitesimally fine particles finding their way into every crevice and seal. Despite wind speeds that might reach 100 kilometers per hour at peak, you'd feel only moderate force because of the thin atmosphere. The most dangerous aspect wouldn't be the wind, it would be the darkness, the cold at night, and the pervasive, inescapable dust. Eventually, every storm ends. The dust begins to settle, first from the lower atmosphere, gradually working upward. Visibility improves. The sun strengthens. Surface features reappear. Within weeks to months, depending on the storm's severity, Mars returns to something approaching its normal state, though with surface details slightly changed, dunes shifted, rocks newly exposed or buried, the landscape subtly rearranged by the global redistribution of dust. The planet has exhaled dust into its atmosphere and inhaled it back down to the surface in a different configuration. And then life on Mars, for the robots that call it home, returns to normal, until the next storm begins to brew and the cycle starts again. This is Mars, a world where dust doesn't just move with the wind, but occasionally rises up to envelop an entire planet in rusty twilight. Journey with me now to the ends of Mars, where eternal winter reigns and ice stretches for hundreds of kilometers in every direction. These are the Martian polar caps, vast frozen realms that crown the planet's north and south poles. But these aren't simple ice sheets like Earth's Arctic and Antarctic. These are dynamic, layered, scientifically precious archives that record millions of years of Martian climate history in frozen strata. They grow dramatically each winter and shrink each summer in a planetary breathing cycle. They contain enough water to cover the entire planet in a global ocean if melted. They preserve evidence of orbital cycles stretching back eons. And they're composed not just of water ice, but of something unique to Mars, frozen carbon dioxide, dry ice existing naturally and permanently on a planetary surface. Let's explore these magnificent frozen poles. The North Polar Cap spreads approximately 1,000 kilometers in diameter during summer, about the distance from Boston to Atlanta. With an average thickness of 2 kilometers and a volume of 1.6 million cubic kilometers, this is a substantial reservoir of frozen water. The permanent cap consists primarily of water ice, the familiar frozen at temperatures that on Mars rarely rise above -60 Celsius even in summer. Each winter, carbon dioxide frost precipitates directly from the atmosphere, adding a thin seasonal veneer 1 to 1.5 meters thick that completely covers the water ice beneath. As spring arrives, this CO-free frost sublimates directly back to gas without ever melting to liquid, and by summer, the permanent water ice cap stands revealed, brilliant white against the rusty Martian terrain. From orbit, the cap shows distinctive dark spiral channels created by seasonal processes we're still working to fully understand. The South Polar Cap presents a fascinating contrast. During summer, it appears much smaller, only 350 to 400 kilometers in diameter, but reaches similar thickness of approximately 3 kilometers and contains roughly 1.6 million cubic kilometers, including adjacent deposits. The South Pole sits at significantly higher elevation, plus 1,000 to plus 3,500 meters, and remains cold enough year-round to retain a permanent layer of 8 meters of solid carbon dioxide ice atop the underlying water ice. Think about that, a permanent deposit of dry ice, carbon dioxide frozen solid at -125 Celsius or colder, existing naturally on the surface of another world. The bright polar cap surface shows approximately 85% KOS and 15% water ice. This COP layer never completely sublimates. It's a permanent feature, unique in our solar system. Each Martian winter brings one of the solar system's most dramatic transformations. As temperatures plunge at the winter pole, carbon dioxide gas in the atmosphere freezes directly into solid dry ice and falls as snow. 3 to 4 trillion tons of atmospheric COS, representing 25 to 30% of Mars's entire atmospheric mass, condenses onto the winter cap. The seasonal cap extends all the way down to 60 degrees latitude in the north and 50 degrees in the south, creating vast temporary ice sheets thousands of kilometers across. Atmospheric pressure drops measurably as this mass leaves the gas phase. When spring arrives and the CO sheet sublimates back into the atmosphere, pressure rises again. Mars breathes in and out with its seasons, the polar caps growing and shrinking in a cycle visible from Earth through modest telescopes, a process that has been occurring for billions of years. The process of seasonal CO sheet sublimation creates unique Martian phenomena, visible nowhere else. Near the South Pole, sunlight penetrates translucent ice slabs, heating the darker basaltic material beneath. Pressure builds underneath the ice as the trapped material heats and releases gas. Eventually, the gas erupts violently through cracks in the ice, carrying dark dust and sand with it. This creates the famous spiders or arenae-form terrain, starbursts, and dark fans radiating across the ice. These patterns appear and evolve rapidly over days to weeks, which is unusual for Martian geological processes. The escaping gas carves radial channels under the ice, creating branching patterns visible from orbit. When the seasonal ice finally sublimates completely, these spider patterns are revealed, etched into the surface beneath, hundreds of them clustered together in otherworldly formations. Look closer at the permanent ice caps with radar and optical instruments, and you'll discover that they're not homogeneous blocks of ice, but finely layered structures, each layer a page in Mars's climate history. The polar layered deposits show alternating bands of relatively pure ice and dustier ice. Layers vary in thickness, composition, and brightness, and these variations correlate with Mars's orbital cycles. Unlike Earth, which has a large stabilizing moon, Mars's axial tilt varies dramatically from roughly 15 degrees to 35 degrees over approximately 120,000-year cycles. When the tilt is higher, poles receive more direct sunlight. Ice sublimates, the atmosphere thickens, and water redistributes toward the equator. When the tilt decreases, ice accumulates at the poles again. Each layer in the ice caps potentially represents one of these cycles, dust content indicating atmospheric dustiness during that period. Radar observations reveal these layers extending deep into the ice, with high and low reflectivity zones matching climate models. Recent research identified an abrupt brightness increase in northern cap layers approximately 400,000 years ago, corresponding to a change in wind direction visible in equatorial dune orientations. This shows connections between polar processes and global climate that we're only beginning to understand. The deepest layers could extend back millions of years, potentially preserving climate information spanning vast timescales. If all the water ice in both polar caps melted, it would create a global ocean 137 meters deep, covering approximately 20% of the planet's surface. Yet isotopic evidence suggests Mars has lost far more water than currently remains. Deuterium enrichment indicates Mars lost 6.5 times the current ice cap volume of water over its history. The caps are remnants of a once much wetter world. Standing on the edge of a Martian polar cap would be an experience of stark, austere beauty. Pure white ice stretching to the horizon in every direction, so bright under the sun that you'd need protection for your eyes. Temperature so cold that exposed skin would freeze in seconds. The sky overhead a deeper shade of pink, the atmosphere slightly thinner at this elevation. In winter, you might witness COP snow falling from high-altitude clouds, crystals of frozen carbon dioxide drifting down through the thin air, sometimes sublimating before reaching the surface in that phenomenon called virga. In spring, you might see the spiders forming, dark geysers erupting through the ice, the surface transforming day by day. These poles aren't dead, they're dynamic, active, breathing with the planet's seasons. They're libraries of climate data, reservoirs of water for future explorers, and beautiful in their own right. As we leave these frozen realms, remember, ice on Mars isn't just frozen water. It's frozen history waiting to be read. Today, liquid water cannot exist on the Martian surface. The atmospheric pressure is too low, the temperature too cold. Any liquid water would instantly freeze or boil away, sublimating directly to vapor without remaining liquid. Yet when we look at Mars through our orbiters and rovers, we see something remarkable and undeniable, the unmistakable fingerprints of flowing water preserved in stone and sediment. Ancient riverbeds wind across the landscape. Delta formations spread where rivers once emptied into long vanished lakes. Minerals that form only in the presence of water are abundant in the rocks. Rounded pebbles speak of tumbling and flowing streams. The evidence is overwhelming, written across the planet in a language geologists know how to read. Mars wasn't always the frozen desert you see today. Billions of years ago, this world had rivers, lakes, perhaps even seas. Join me as we trace the story of water on Mars, from the ancient past to the discoveries being made right now. Our best evidence for ancient water comes from Jezero Crater, where NASA's Perseverance rover has been exploring since February 2021. Jezero contains a prominent ancient river delta where water once flowed into what was a lake 3.5 billion years ago. Picture it. A river called Neretva Valles, 400 meters wide, carrying sediment-laden water down into a crater that held a standing body of water for millions or perhaps even billions of years. The delta formation is obvious from orbit, a fan-shaped deposit of layered sediments exactly matching deltas on Earth where rivers meet standing water. Perseverance has been climbing through these delta deposits, examining rocks that formed in that ancient lake environment. The rover has found wave ripples preserved in mudstone dating to 3.7 billion years ago, the clearest evidence yet of open water bodies where waves lapped against shores. Not far away, Curiosity has been exploring Gale Crater since August 2012, and its findings complement Perseverance's discoveries. Gale Crater once held extensive lake systems. Curiosity has found evidence that these lakes persisted for millions to billions of years, providing a stable, wet environment. The rover has climbed Mount Sharp, a mountain of layered sediments in Gale's center, essentially climbing through time, with each layer representing a different era in the crater's history. Curiosity has found fine-grained mudstones deposited in quiet lake waters, sulfate minerals left when water evaporated, and the wave ripples I mentioned earlier. These ripples are particularly special. They're preserved exactly as they formed billions of years ago when water gently disturbed the sediment. Running your hand over these rocks, if you could, you'd feel the texture of ancient waves frozen in stone. Minerals tell stories chemistry alone can reveal. Perseverance's Pixel instrument has identified clay minerals including nontronite and saponite in Jezero rocks. These phyllosilicates form only in the presence of water, as water interacts with volcanic rocks over extended periods. The rover has found sulfate minerals indicating evaporation of salty, acidic water. Carbonate minerals rich in magnesium and iron formed through aqueous processes. But here's what's fascinating. The chemistry shows multiple periods with different water conditions. Early water was hot and acidic. Then, conditions shifted to neutral pH and cooler temperatures. Finally, the environment became alkaline and cold. These weren't random changes. This represents a progression toward increasingly habitable conditions over time. The planet was becoming more suitable for life, not less, at least in Jezero Crater, before the water finally disappeared entirely. Evidence of water isn't limited to a few locations. Valley networks resembling dried river systems cover large portions of Mars's ancient terrain. These networks show branching patterns exactly like Earth's rivers, with tributaries joining into larger channels that flow downslope toward lower elevations. Outflow channels, some of the largest in the solar system, appear carved by catastrophic floods that dwarfed anything on Earth. Hesperia planum and other regions show extensive networks. The Chrysoplanitia basin received water from multiple massive channels. These features couldn't form without flowing water, and not just a little water, but sustained flows over extended periods or catastrophic releases of staggering volumes. The planet's surface is literally carved by the action of ancient water, the evidence so clear that early observers with primitive telescopes thought they saw canals, misinterpreting natural formations but correctly intuiting that water had shaped this world. Water exists on Mars today, but hidden from view. NASA's InSight lander, which operated from 2018 to 2022, used seismic data to reveal something remarkable. A zone of fractured rock 11.5 to 20 kilometers below the surface is filled with liquid water. This deep crustal water reservoir may contain volumes exceeding those proposed for ancient Martian oceans. It's the first confirmed detection of liquid water on Mars, but you couldn't access it without drilling technology far beyond what we currently possess. The water is trapped in tiny cracks and pores in the rock, under pressure, possibly salty enough to remain liquid at cold temperatures. It might represent water that soaked into the crust billions of years ago when the surface was wet, becoming trapped as the surface froze and dried. Somewhere deep beneath your feet on Mars, in the dark and the cold, liquid water still flows through fractured stone. So what happened? How did Mars transform from a world with flowing rivers and standing lakes to the frozen desert we see today? The answer is complex and still being refined, but the basic story is clear. Mars's smaller size meant its interior cooled faster than Earth's. When the core cooled, the global magnetic field shut down. Without magnetic protection, the solar wind began stripping the atmosphere away. As atmospheric pressure dropped, liquid water could no longer remain stable on the surface. Some water evaporated and was lost to space. Some soaked into the porous soil and froze as permafrost. Some became trapped in the deep subsurface reservoir. The planet grew colder as greenhouse gases were lost. Eventually, Mars crossed a threshold from which it couldn't return. The surface became too cold and the pressure too low for liquid water. The rivers stopped flowing. The lakes froze and then sublimated away. Water became locked underground or in polar ice. The story of water on Mars is ultimately a story of planetary evolution, climate change on a geological scale, and lost habitability. But it's not a story of total loss. The water didn't completely disappear, it transformed and hid. It's locked in polar ice caps holding enough water to cover the planet in a shallow ocean. It's trapped as permafrost in the soil. It flows in fractured rock kilometers below the surface. And most importantly for our purposes, it left behind detailed evidence of its presence, minerals, sediments, erosional features, and potentially, as we're about to discover, the fossilized remains of life itself. Mars was habitable? The question that drives exploration today isn't whether the conditions for life existed, but whether life actually arose to take advantage of those conditions. And incredibly, we may finally be on the verge of answering that question. September 2025 will be remembered as a watershed moment in the history of science and human exploration. That month, NASA announced peer-reviewed findings in Nature Journal that acting NASA Administrator Sean Duffy called the closest we have ever come to discovering life on Mars. The discovery was made by the Perseverance rover in a rock sample called Sapphire Canyon from a formation known as Shayava Falls, an arrowhead-shaped rock just over 3 feet long collected in July 2024 from the ancient Neretva Valles river valley. High-resolution imaging revealed something extraordinary, distinctive patterns at millimeter scale that scientists call leopard spots, colorful minerals arranged in reaction fronts with sub-millimeter nodules. But it wasn't just the pattern, it was the chemistry. This rock contains organic carbon, sulfur, oxidized iron, and phosphorus. And most remarkably, it contains specific minerals that, on Earth, are often associated with microbial life. Let me explain what makes this discovery so significant. The rock contains vivianite, a hydrated iron phosphate mineral that on Earth frequently forms in sediments around decaying organic matter. It also contains greigite, an iron sulfide that certain forms of microbial life produce on Earth. But it's the pattern that really caught scientists' attention. The leopard spots appear to have formed through electron transfer reactions between sediment and organic matter. On Earth, these kinds of reaction fronts often indicate microbial activity, with microbes using the chemical reactions to generate energy for metabolism. The rocks show no evidence of the high temperatures or acidic conditions that might produce similar minerals through non-biological processes. Instead, everything about this sample suggests it formed in relatively cool, water-rich conditions that, on Earth, would be ideal for microbial life. The chemistry, the minerals, the patterns all align. Important caveats exist, and scientists are careful to express them. Abiotic explanations, processes that don't involve life, cannot be definitively ruled out without further study. The sample needs to be returned to Earth for detailed laboratory analysis with instruments far more sophisticated than any rover can carry. Earth-based laboratories can conduct isotopic analysis to determine the source of organic carbon, use advanced spectroscopy to map mineral distributions at nanometer scale, search for preserved cellular structures, analyze the pattern of organic molecules for biosignatures, and subject the sample to every test that might distinguish biological from abiotic origins. The Mars sample return mission, despite its challenges, has never been more critical. That single rock, along with the 32 other samples Perseverance has collected, needs to come home. It may contain the proof we seek, yet even with caveats, this represents the strongest potential biosignature ever discovered on another world. The finding scores highest on the confidence of life detection scale used to evaluate such claims. And, surprisingly, this discovery comes from relatively young sedimentary rocks. Earlier hypotheses assumed biosignatures would be confined to the oldest formations from Mars's wet period. The fact that these minerals appear in younger sediments suggests Mars may have remained habitable longer than previously thought. Perhaps life arose early and persisted for 1 billion years or more as conditions slowly deteriorated. Perhaps the last refugia for Martian life existed in locations like Jezero Crater long after other regions had dried completely. We're discovering that Mars's habitable period wasn't a brief flash, but potentially an extended era, giving life, if it arose, plenty of time to establish itself. Perseverance's discovery complements findings from its older sibling, Curiosity. In March 2025, Curiosity announced the discovery of the heaviest organic molecules ever found on Mars: decane, undecane, and dodecane, long-chain hydrocarbons with up to 12 consecutive carbon atoms. These appear to be fragments of fatty acids, specifically undecanoic, dodecanoic, and tridecanoic acids. On Earth, fatty acids are chemical building blocks of life, forming cell membranes and serving crucial biological functions. Whether the Martian compounds have biological or abiotic origins remains unknown, but their presence in 3.5 billion-year-old mudstone from Gale Crater's ancient lakebed demonstrates that complex organic chemistry occurred on ancient Mars. The building blocks were there. The environment was suitable. The question isn't whether Mars could have supported life. It's whether life actually arose. Both rovers have confirmed that ancient Mars had everything life requires. Liquid water is confirmed through multiple lines of evidence we've discussed. Chemical building blocks, including diverse organic molecules and fatty acid fragments, have been found. Energy sources from chemical reactions and redox processes were abundant. protective environments existed in lake sediments and clay-rich rocks, sheltering potential life from harmful radiation. Neutral to alkaline pH conditions developed over time in multiple locations. Essential elements including carbon, nitrogen, oxygen, phosphorus, and sulfur were all present and available. The checklist for habitability is complete. Mars 4 billion years ago wasn't just potentially habitable in theory, it was demonstrably habitable in practice, with specific locations offering all the requirements for life as we understand it. The conditions were met. The stage was set. The question is whether the play began. Scientific consensus holds that Mars was habitable approximately 4.48 billion years ago, potentially 500 million years before the earliest known Earth life. Think about that. Mars may have become habitable before Earth did. The habitable period extended through the Noachian period from 4.1 to 3.7 billion years ago, and possibly into the late Hesperian age around 3 billion years ago. This provides a window of 500 million to potentially 1 billion years when conditions suitable for life persisted. Liquid water existed in crater lakes for millions of years, and probably much longer, sufficient time for life-forming chemistry to occur. Mars preserves its geological record better than Earth due to lacking plate tectonics. Ancient Martian rocks remain relatively undisturbed at the surface, making Mars potentially a better archive of early solar system conditions than our own heavily processed planet. As we sit here now in 2025, we find ourselves at an extraordinary moment in human history. For thousands of years, philosophers wondered if life existed beyond Earth. For hundreds of years, scientists speculated. For decades, we've been actively searching. And now, we may have found it. Or at the very least, we've found the strongest evidence yet that life could have existed on Mars billions of years ago. We don't have definitive proof yet. We need those samples returned. We need further analysis. But the evidence is mounting, the case is strengthening, and the possibility is becoming more plausible with each discovery. Whether Sapphire Canyon contains fossil microbes or abiotic minerals, whether life arose on Mars or remained only chemistry, we're asking the right questions in the right places with the right tools. And that, after all these years of wondering, is itself remarkable. Look up from the Martian surface at night, and you'd see something unexpected in the sky, 2 moons, neither of them particularly moon-like. These aren't the large, spherical, crater-pocked worlds we're familiar with from our own moon or the gas giant moons of the outer solar system. These are Phobos and Deimos, Mars's mismatched pair of captured companions, 2 dark, potato-shaped bodies that tumble and orbit in ways unlike any other moons. Phobos, the larger inner moon, circles so close to Mars that it rises in the west and sets in the east, opposite to normal celestial motion, completing 3 orbits per Martian day. Deimos, the smaller outer moon, orbits so slowly it takes 2.7 days to set, appearing almost stationary in the sky. They're irregular, cratered, mysterious, and their origin remains one of the solar system's unsolved puzzles. Let's meet Mars's strange companions. Phobos is the larger of the pair, measuring 27 by 22 by 18 kilometers, roughly the length of a large city but far from spherical. With a mean radius of 11 kilometers, this irregular body orbits just 6,000 kilometers above Mars's surface, closer to its planet than any other moon in the solar system. At this proximity, Phobos experiences powerful tidal forces from Mars. The moon completes an orbit in just 7 hours and 39 minutes, meaning it circles Mars 3 times per Martian day. From Mars's surface, Phobos appears roughly 1/3 the width of Earth's moon, crossing the sky in just 4 hours and 15 minutes or less before setting again. It moves so fast you could watch it visibly change position over the course of an evening. In polar regions above 70 degrees latitude, Phobos never appears above the horizon at all. Phobos bears the scars of a near-catastrophic collision. Stickney crater, measuring 9 to nearly 10 kilometers in diameter, dominates almost half of Phobos' surface. This impact nearly shattered the entire moon. The crater appears filled with fine dust, and boulders can be seen sliding down its slopes. The impact was so powerful that mysterious grooves and streaks radiate across Phobos' surface from the impact site. These grooves typically measure less than 30 meters deep, 100 to 200 meters wide, and extend up to 20 kilometers in length. Scientists think they formed either from boulders ejected by the Stickney impact that rolled across the surface leaving tracks, or they represent stress fractures, essentially stretch marks, as Mars's tidal forces slowly pull Phobos apart. With a density of 1.88 grams per cubic centimeter and porosity of 25 to 35%, Phobos is essentially a rubble pile, barely held together. With an albedo of just 0.071, Phobos ranks among the darkest objects in the solar system, reflecting less light than coal. This darkness, combined with its spectral characteristics, suggests a composition similar to carbonaceous chondrite asteroids. But here's where things get truly fascinating. Phobos is spiraling inward toward Mars at a rate of 1.8 to 2 meters per century. Tidal forces are gradually stealing the moon's orbital energy, causing it to slowly fall. In 30 to 50 million years, Phobos will meet one of two fates. It will either crash directly into Mars in a spectacular impact, or more likely, it will cross what's called the Roche limit and be torn apart by tidal forces, creating a temporary ring system around the red planet. Mars will have rings, made from the shattered remnants of its closest moon. But that's millions of years in the future. For now, Phobos still orbits, still rises in the west, still tumbles through space. Deimos, the outer moon, is roughly half the size of Phobos, measuring 15 by 12 by 11 kilometers. It orbits at 23,460 kilometers from Mars's center, taking 30 hours and 18 minutes to complete an orbit. Unlike its companion, Deimos rises in the east and sets in the west like a normal moon, though so slowly that it takes 2.7 days to set as it gradually falls behind Mars's rotation. From the Martian surface, Deimos appears almost star-like, about 1/12 the width of Earth's moon, more of a bright point than a disk. You'd need a telescope to see it as anything other than an unusually bright, slowly moving star. Deimos is the smaller, fainter, more distant sibling, easy to overlook but no less mysterious for its subtlety. Deimos appears much smoother than Phobos, not because it experienced fewer impacts, but because it's covered by a thick regolith layer, possibly as deep as 100 meters, that has filled in its craters over time. The largest craters, Swift and Voltaire, reach approximately 3 kilometers in diameter. Here's something fascinating about Deimos's regolith. When impacts occur, the ejected material easily escapes the moon's weak gravity, but remains captured in Mars' orbit. Eventually, this material falls back onto Deimos as dust, gradually filling the craters and smoothing the surface. Unlike Phobos, Deimos lacks prominent grooves. And while Phobos spirals inward toward destruction, Deimos is slowly moving away from Mars. Eventually, in the distant future, it may escape Mars's gravity entirely and become an independent body orbiting the Sun. The two moons are heading in opposite directions, toward opposite fates. The origin of these moons remains one of Mars exploration's enduring mysteries. Both resemble carbonaceous chondrite asteroids in composition, spectra, albedo, and density, suggesting they were captured from the asteroid belt. Yet their nearly circular orbits in Mars's equatorial plane contradict typical capture scenarios, which usually produce eccentric, highly inclined orbits. Phobos's high porosity and surface minerals matching Mars's own phyllosilicates suggest instead a giant impact origin, similar to how Earth's moon formed. Perhaps a Ceres divesticized object impacted Mars billions of years ago, creating a debris ring that coalesced into moons. A 2024 study offers another scenario. An asteroid passed too close during a flyby, and Mars's gravity disrupted it, creating hundreds of thousands of fragments. over half ejected into space, while remaining fragments collided and settled into a disk that formed both moons. This better accounts for Deimos's large orbital radius. In 2026, Japan's MMX mission will launch to visit Phobos, land on its surface, collect samples from multiple locations, and return them to Earth in 2031. This will be the first sample return from a moon other than our own, and it may finally resolve the mystery of Phobos and Deimos's origins. Are they captured asteroids? Impact debris? Ooh, disrupted flyby remnants? The answer lies in the chemistry and isotopic composition of their material, data we can only obtain with Earth-based laboratory analysis of returned samples. As we leave these mysterious moons behind, take one last look at them in your mind's eye. Phobos rising in the west, racing across the sky 3 times a day, doomed to eventual destruction. Deimos rising in the east, slow and subtle, gradually escaping its planet's embrace. 2 small, dark, potato-shaped companions, adding to the alien beauty of the Martian sky, reminders that every world has its own unique characteristics, its own story to tell. We've never walked on Mars ourselves, not yet, but we've sent our eyes, our hands, our curiosity in mechanical form. Right now, as you listen to these words, 2 car-sized rovers are exploring Mars, drilling into rocks, analyzing chemistry, taking photographs, searching for evidence of ancient life. 7 spacecraft orbit overhead, mapping the surface, studying the atmosphere, serving as communication relays. A grounded helicopter sits on the surface, its mission complete but still functioning as a weather station. Mars is more heavily explored by robotic emissaries than any other planet besides Earth. We've been sending missions there for 6 decades, and each one has revealed something new, something unexpected, something that changed our understanding. Join me now as we meet the robots that represent humanity on the surface of another world, our tireless explorers working in an environment that would kill a human in minutes. Perseverance, operating in Jezero crater since February 2021, is our most sophisticated Mars explorer. This rover has collected 33 of its 43 available sample tubes, including the potentially life-containing Sapphire Canyon sample we discussed earlier. But collection is just part of the mission. Perseverance carries an unprecedented suite of scientific instruments, cameras that can resolve features smaller than a grain of sand, a ground-penetrating radar to probe subsurface layers, an X-ray spectrometer that can analyze rock chemistry without touching it, a sophisticated drill that can extract pristine core samples from deep within rocks. As of October 2025, the rover has traveled over 20 miles, climbed 1,640 vertical feet to crest Jezero crater's rim, and operated for over 1,600 Martian days. And it's still going strong, now exploring the Northern Rim campaign, studying rocks ejected from deep within Mars when the crater formed nearly 4 billion years ago. Not far away in geological terms, but across a vast distance on the actual surface, Curiosity continues its mission that began in August 2012. This rover has now operated for over 13 years, far exceeding its original 2-year mission timeline. Curiosity has traveled 22 miles and climbed over 1,000 feet up Mount Sharp, essentially climbing through billions of years of Martian geological history as it ascends the layered sediments. The rover's discoveries include the heaviest organic molecules found on Mars, wave ripples preserved in ancient lake sediments, evidence that Gale Crater once held standing water for millions to billions of years, and carbonates providing insights into Mars's ancient carbon cycle. In August 2025, Curiosity received new autonomy and multitasking capabilities, making it more efficient than ever. All systems remain operational, and the rover has sufficient fuel reserves for years of continued exploration. Curiosity just keeps going, keeps discovering, keeps revealing Mars's secrets. April 19, 2021 marked a Wright brothers moment when Ingenuity, a 1.8 kilogram helicopter, achieved the first powered controlled flight on another planet. Designed for just 5 flights over 30 days, Ingenuity exceeded all expectations by completing 72 flights over nearly 3 years. The tiny helicopter logged 128 minutes of flight time, traveled over 10 miles, reached altitudes of nearly 80 feet, and served as an aerial scout for Perseverance. Its longest single flight covered 704 meters. Flying in Mars's thin atmosphere, only about 1% of Earth's density, required spinning the rotor blades at an incredible 2,400 RPM. On January 18, 2024, Flight 72 ended the mission when a navigation system failure caused a hard landing that snapped off all 4 rotor blades. Though permanently grounded, Ingenuity remains operational as a weather station, potentially collecting data for up to 20 years, waiting for future missions that might retrieve its information. Overhead, 7 orbiters maintain constant vigil. Mars Odyssey, launched in 2001, is NASA's longest-serving Mars mission at 24 years and counting, primarily serving as a critical communications relay while detecting vast hydrogen deposits indicating subsurface water ice. Mars Reconnaissance Orbiter carries HiRISE, achieving resolution sufficient to identify dinner table-sized objects from orbit, and has returned over 450 terabits of data. MAVEN studies atmospheric escape, revealing how Mars loses atmosphere to solar wind. Mars Express, Europe's contribution, launched in 2003, recently received software updates potentially extending operations until 2034. The UAE's HOPE probe provides unprecedented full-disk atmospheric observations from its unique high orbit. TRACE Gas Orbiter maps atmospheric composition. China's Tianwen D1 continues operations despite communication difficulties. These orbiters are more than observation platforms. They're the communication backbone that allows surface missions to send their data home. These missions represent humanity's presence on another world, but they operate in an environment extraordinarily hostile to electronics. Temperatures swing from pleasant to lethal within hours. Dust storms can block sunlight for weeks. Cosmic radiation constantly bombards the surface. Communication with Earth has delays up to 20 minutes, one way, making real-time control impossible. Rovers must be semi-autonomous, making decisions on their own about where to drive, what to photograph, which rocks to analyze. They navigate hazards, manage their own power, diagnose their own problems. In many ways, they're not just machines, they're robotic geologists, exploring Mars with a degree of independence we rarely give our technological creations. And they've performed magnificently, far exceeding their design lifetimes, surviving dust storms, equipment failures, and the harsh Martian environment to continue their missions year after year. Each mission builds on lessons from its predecessors. Sojourner in 1997 proved rovers could work on Mars. Spirit and Opportunity, operating from 2004 to 2010 and 2018 respectively, proved rovers could explore for years, not just months. Curiosity demonstrated that complex instruments could analyze Martian rocks with laboratory-grade precision. Perseverance added sample collection capability, sterile handling to avoid contaminating samples, and the first Mars helicopter. Each generation more capable, more sophisticated, more able to answer the profound questions we're asking. Future missions will continue this progression. The European ExoMars rover with its 2-meter drill to access deep, protected samples, Japan's MMX mission to return samples from Phobos, China's Tianwen 3-sample return. We're building toward the ultimate goal, bringing Martian material to Earth for analysis in our finest laboratories, and eventually sending humans to continue the exploration our robots have begun. When the history of human exploration is written, this era will be remembered as the time when we first sent our ambassadors to another world, and they thrived there. These rovers and orbiters, these mechanical explorers, represent our curiosity made manifest. They're our eyes seeing alien sunsets, our hands touching ancient rocks, our minds analyzing chemistry that existed before life arose on Earth. They work in silence and cold and isolation, millions of miles from the nearest help, yet they persist. They explore. They discover. And they send back evidence of a world that was once habitable, evidence of a past we're only beginning to understand, evidence that we might not be alone. These robots, these magnificent machines, are writing the first chapters of humanity's story on Mars. And the story they're telling is more fascinating than anyone imagined. Our journey across Mars is nearing its end, but Mars's story and humanity's relationship with this world is just beginning. 6 decades of exploration have transformed Mars from a mysterious point of light into a world we know in exquisite detail. We've mapped its surface, measured its atmosphere, analyzed its rocks, detected its subsurface water, and potentially discovered evidence of ancient life. Yet each answer raises new questions. Each discovery opens new avenues of investigation. And now we stand at a threshold, the transition from robotic exploration to human presence, from studying Mars at a distance to walking on its surface ourselves. The future of Mars exploration is extraordinarily exciting, and it's closer than you might think. Join me as we look ahead to what comes next for the red planet, and for those of us dreaming of setting foot on its rust-red soil. The most immediate challenge is returning the samples Perseverance has collected. The Mars Sample Return mission faces budget challenges and uncertain timelines, but its scientific importance cannot be overstated. Those 33 sample tubes contain material that might definitively answer whether life ever existed on Mars. Earth laboratories can conduct isotopic analysis, advanced spectroscopy, searches for cellular structures, and countless other tests impossible to perform with rover instruments. The samples represent diverse environments, ancient lake sediments, river delta deposits, impact-ejected rocks from deep in the crust, and the potentially life-bearing Sapphire Canyon sample. Together, they're a cross-section of Mars's past. If the NASA ESA mission faces further delays, China's Tianwen-3, launching in late 2028, could return Mars samples by July 2031, potentially becoming the first Mars sample return. Either way, by the early 2030s, we should have Martian material in Earth laboratories for the first time. Future robotic missions promise even greater discoveries. The European Space Agency's ExoMars, Rosalind Franklin rover, revived after suspension and now planned for a late 2028 launch with NASA contributions, will carry a 2-meter drill, the deepest drilling capability of any Mars mission. This will access subsurface samples better protected from radiation and more likely to preserve biosignatures if they exist. The rover will search specifically for signs of life, past or present. Japan's MMX mission, launching in 2026, will visit Phobos, collect samples from multiple locations on the Moon's surface, and return them to Earth in 2031. These samples will finally reveal whether Phobos and Deimos are captured asteroids, impact debris, or something else entirely. Each mission targets a different aspect of Mars's mysteries, and each brings us closer to comprehensive understanding of this complex world. But the most ambitious plans involve sending humans to Mars. NASA targets human Mars missions in the 2030s, with the Artemis Moon program serving as a testing ground for Mars technologies. The challenges are extraordinary. A journey of over 1 billion miles round trip, mission duration of 2 to 3 years, communication delays up to 20 minutes, one-way preventing real-time mission control, launch windows only every 26 months, intense radiation exposure during transit, and on the surface, need for life support systems that can function independently for years, and the requirement to produce fuel, oxygen, and water from Martian resources for the return journey. These aren't insurmountable problems, they're engineering challenges that demand innovation, resources, and commitment. Multiple agencies and companies are developing solutions, from advanced propulsion systems to Mars habitats to in-situ resource utilization technologies. SpaceX pursues the most aggressive timeline. Elon Musk plans to launch 5 uncrewed starships to Mars in the late 2026 launch window, carrying Tesla Optimus humanoid robots to test landing reliability. If successful, first crewed missions could follow in 2028 or 2029, though 2021 appears more realistic. The long-term vision envisions exponential growth, 5 ships in the initial window, approximately 20 missions in 2028-29, 100 missions in 2038-31, and potentially 500 missions by 2033. The goal is establishing a self-sustaining city within 20 years. These timelines remain highly ambitious given current technology readiness. Starship requires successful development of orbital refueling, heat shields capable of surviving Mars entry, propellant production using Martian resources, advanced life support, and landing precision. Recent test flights have experienced setbacks, yet progress continues, and each test brings the technology closer to readiness. What would life be like for the first humans on Mars? They'd wake in pressurized habitats, never able to step outside without a spacesuit. Gravity would feel strange at 38% of Earth's, enough to walk but light enough to feel constantly off balance. The sky would be pink. Sunsets would glow blue. The sun would appear 2/3 the size it does from Earth, providing less warmth and light. Communication with home would involve constant delays. Conversations with Earth-based mission control would be impossible, every exchange requiring 40 minutes for question and answer. Dust would be everywhere, requiring airlocks and constant vigilance against contamination. Growing food in Martian greenhouses, extracting water from ice, producing oxygen from atmospheric geodephy would be daily necessities, not technological demonstrations. It would be difficult, isolating, dangerous, and absolutely fascinating. The first Mars residents would be pioneers in the truest sense. Some envision going beyond mere habitation to terraforming Mars, transforming it into an Earth-like world with breathable atmosphere, liquid water on the surface, and possibly even ecosystems. Proposals include releasing greenhouse gases to warm the planet, importing volatiles from comets or asteroids, using giant mirrors to heat the poles and release trapped KOC, creating atmosphere, producing factories, and introducing specially engineered organisms to begin producing oxygen. These ideas range from theoretically possible to wildly speculative, and the timescales involved would be centuries to millennia. Even if technically feasible, terraforming raises profound ethical questions. Do we have the right to deliberately alter an entire world? What if we destroy evidence of past or present life in the process? Would terraformed Mars remain scientifically valuable? These questions have no easy answers, but they're worth pondering as we consider Mars's long-term future and our role in shaping it. Whether we terraform Mars, establish permanent settlements, or simply continue studying it with increasingly sophisticated robots, one thing seems certain: Mars will be part of humanity's future. This is no longer speculation, it's planning. Missions are being designed. Spacecraft are being built. Technologies are being tested. Astronauts are being trained. The question isn't whether we'll send humans to Mars, but when and what they'll find when they arrive. Perhaps they'll discover definitive evidence of ancient life. Perhaps they'll find surviving microbes in subsurface aquifers. Perhaps Mars will remain a beautiful, dead world that nonetheless teaches us about planetary evolution, climate change, and our place in the cosmos. Whatever we find, the journey itself will be transformative, expanding human presence beyond Earth for the first time since we evolved, making us truly a multi-planet species. Mars is waiting, patient as it's been for billions of years, ready to reveal its final secrets to those brave enough to make the journey. As our journey draws to a close and we prepare to return to Earth in our minds, take a moment with me to reflect on everything we've discovered together. We've explored towering volcanoes that dwarf mountains on Earth, canyons that stretch across continents, polar ice caps that record millions of years of climate history. We've traced ancient rivers now dry, examined evidence of lakes that vanished billions of years ago, and considered the possibility that life once flourished in those waters. We've met Mars's mysterious moons, watched dust storms envelope an entire planet, and marveled at the robots that serve as our eyes and hands on this alien world. Mars has revealed itself to us not as a simple, dead planet, but as a complex world with a rich past, a dynamic present, and an uncertain but fascinating future. What does all this mean? What can Mars teach us about our own world, our own future, and our place in the universe? Mars teaches us first about planetary fragility. This world was once warm and wet, with a thick atmosphere, flowing water, and conditions suitable for life. Then it lost its magnetic field, its atmosphere was stripped away, its water disappeared, and it transformed into a frozen desert. This transformation wasn't catastrophic in human timescales, it took millions of years. But it was inexorable. Mars shows us that habitability isn't permanent. A planet can lose the very qualities that make life possible. This lesson carries profound implications for Earth. Our magnetic field protects our atmosphere. Our distance from the sun keeps us in the habitable zone. Our plate tectonics recycle carbon and regulate climate. These factors aren't guaranteed forever. Mars reminds us that the conditions we take for granted are precious, fragile, and worth protecting. It's a cautionary tale written in rust and ice. Mars also teaches us about climate change. The planet's climate has varied dramatically over geological time due to changes in its orbital parameters and axial tilt. The polar ice caps record these cycles. Dust storms redistribute material globally. The atmosphere thickens and thins with seasonal CO2 deposition and sublimation. Mars shows us what dramatic climate variation looks like on a planetary scale, and it's not gentle. While Earth's climate changes are driven by different mechanisms, Mars provides a laboratory for understanding how planetary climates work, how they can change, and what feedback loops might accelerate or mitigate those changes. The more we understand about Mars's climate history, the better we understand climate science in general, including on our own world. Mars is a climate science textbook, its lessons written in ice and sediment and atmospheric composition. Perhaps most profoundly, Mars teaches us about life's possibilities and limits. If the Sapphire Canyon sample truly contains evidence of ancient life, it would prove that life can arise independently on different worlds. It would suggest that wherever conditions permit, life finds a way to begin. This would imply that life might be common throughout the universe, arising on countless worlds around countless stars. Even if Mars proves to have always been lifeless despite billions of years of habitable conditions, that too teaches us something important, that life, even when conditions are favorable, isn't inevitable. Either answer to the question, was there life on Mars, has profound philosophical implications. Either we're part of a biological universe where life emerges readily, or life is rare and precious beyond measure. Mars holds the answer to one of humanity's deepest questions, and we're tantalizingly close to discovering it. Mars teaches us about exploration itself. 6 decades of missions have shown that space exploration isn't easy or cheap or quick. It requires sustained commitment, billions of dollars, thousands of brilliant minds working together, and patience to see results over years and decades. Yet the returns are immeasurable, scientific knowledge that reshapes our understanding, technological innovations that improve life on Earth, inspiration for new generations of scientists and engineers, and expansion of human presence beyond our cradle world. Every image from Mars, every discovery, every successful landing represents human ingenuity, perseverance, and the drive to explore beyond our immediate surroundings. Mars exploration reminds us what we can achieve when we commit to ambitious goals that transcend national boundaries, political cycles, and short-term thinking. It's proof that humanity can work together towards something greater than ourselves. Mars teaches us about time. The geological features we've explored, the ancient riverbeds, the towering volcanoes, the deep canyons formed over billions of years. Mars forces us to think in timescales beyond human comprehension. The leopard spots in that potentially life-bearing rock formed 3.5 billion years ago, when Earth itself was young and life here had barely begun. The volcanoes grew slowly over hundreds of millions of years. The atmosphere took millions of years to strip away. This deep time perspective is humbling. It reminds us that our entire human history, from the first civilizations to our space age, is a blink in geological terms. Yet in that blink, we've gone from wondering about lights in the sky to landing robots on other worlds and planning to walk there ourselves. Mars's ancient past and our rapid present create a fascinating juxtaposition. Most of all, Mars teaches us to look outward. For most of human history, we were confined to Earth, to our immediate surroundings, to our local concerns. But in the last few decades, we've begun to see ourselves as part of a larger cosmos. Mars is our closest neighbor where human presence is conceivable. It's the first step toward becoming an interplanetary species. Whether we establish permanent settlements there or simply continue studying it from afar, Mars expands our horizons literally and metaphorically. It reminds us that Earth isn't the only world, that we're part of a solar system, a galaxy, a universe filled with planets and stars and possibilities. Looking at Mars, we see not just another world, but a mirror reflecting what Earth might become, what Earth once was, and what we might accomplish if we dare to dream beyond our blue sky. As I think about everything we've discovered together on this journey, I'm struck by a simple truth. Mars isn't just a planet. It's a question. It asks us whether we're alone, whether life emerges easily or rarely, whether our world's habitability is guaranteed or fragile. It asks us whether we'll remain on one world or spread to others. It asks us to imagine futures beyond our current limitations and to work toward making those futures real. Mars challenges us to be curious, to explore, to question, to learn, to persist in the face of vast distances and difficult problems. And in rising to that challenge, in sending our robots to this alien world and planning to follow them ourselves, we're answering Mars's questions with questions of our own. What can we discover? What can we achieve? What can we become? The conversation between humanity and Mars has only just begun, and I, for one, cannot wait to hear what comes next. Our journey to Mars concludes here, but the real exploration continues. Right now, at this very moment, perseverance and curiosity are examining rocks, taking photos, searching for answers. Orbiters are mapping terrain and studying atmosphere. Engineers are designing the missions that will return samples to Earth and send humans to walk on Martian soil. The story of Mars and humanity is still being written, and you're living in the era when the most profound chapters are unfolding. Thank you for joining me on this relaxing journey to the Red Planet. I hope it brought you peace, sparked your curiosity, or helped you find rest in the wonders of our cosmic neighborhood. If you enjoyed this voyage, consider subscribing to Cosmic Calm for more serene journeys through the universe. The cosmos is vast, beautiful, and filled with mysteries waiting to be explored. Until our next journey together, look up at the night sky, find that rust-red point of light that is Mars, and remember, we've been there. We're there right now, and someday soon we'll walk there ourselves. Sweet dreams, fellow explorer.